This video is a continuation of our previous video, which is about integration of rational functions by partial fractions. And in the previous video, we have discussed the two cases wherein the denominator of the rational functions can be factored into linear factors. So in this video, we will be discussing the last two cases wherein the denominator of our rational functions can be factored into distinct irreducible quadratic factors. So what do we mean by irreducible quadratic factors? This is a quadratic factor which cannot be anymore factored into linear factors wherein the coefficients are rational numbers. So when the denominator of the proper rational function is factorable into distinct irreducible quadratic factors where none of the irreducible factor is repeated, then this belongs to case number 3. So in this example, let us first factor our denominator. And since in this example, the degree of the numerator is 3, which is less than the degree of the denominator, which is 4, then this is a proper fraction. Then therefore, we can factor our denominator here, which have a common monomial factor of x. So this is x times x cubed minus 4x squared plus 4x minus 1. And of course, we have the numerator of 5x cubed minus 16x squared plus 12x minus 2 here. And factoring further this one, we have x times x minus 1 times x squared minus 3x plus 1. And of course, we have the numerator, which is 5x cubed minus 16x squared plus 12x minus 2 here. And you can obtain these factors by dividing this one by this factor x minus 1. And you can check that the quotient is this. Now that we have factored already the denominator, wherein one of the factor is a quadratic factor which cannot be reduced anymore to a product of two linear factors where the coefficients are rational numbers, then this example belongs to case number 3, where you can find distinct irreducible quadratic factors. And since this is a proper fraction already, we can convert this one to its equivalent partial fractions, which is a over x for this factor here, and added to b over x minus 1 for this factor here. And for the next factor, which is the quadratic x squared minus 3x plus 1, this is over x squared minus 3x plus 1. But in the numerator, our constant will be multiplied by its derivative, which is 2x minus 3. And this will be added also to the constant d, wherein the denominator is also this quadratic x squared minus 3x plus 1. So this is now our partial fractions for this proper rational function. And you notice that you have here two partial fractions corresponding to this one quadratic factor, because in the first partial fraction, we have a factor in the numerator which is the derivative of this quadratic factor. And in the second one, it's just a constant without a derivative in the numerator. Now, our next goal is to find the values of a, b, c, and d in our partial fractions. So we write this proper rational fraction as 5x cubed minus 16x squared plus 12x minus 2, and this is divided by these factors of x times x minus 1 times x squared minus 3x plus 1, and this is equal to our partial fractions, which are a over x and added to b over x minus 1 plus c times 2x minus 3 over this quadratic of x squared minus 3x plus 1 plus d over the quadratic factor of x squared minus 3x plus 1 here. And to eliminate these denominators here, we need to multiply both sides of the equation by the least common denominator, which is x times x minus 1 times x squared minus 3x plus 1 here. And multiplying all of this with this fraction here, the whole denominator will be cancelled by this one. So what remains is 5x cubed minus 16x squared plus 12x minus 2, which is equal to a times x minus 1 times x squared minus 3x plus 1 here, because this x and this x cancels each other, plus b times x squared minus 3x plus 1, because this x minus 1 and this x minus 1 cancels each other. And this is also added to c times 2x minus 3 times x minus 1, and plus d times x minus 1. Now multiplying these factors here, we have 5x cubed minus 16x squared plus 12x minus 2, which is equal to a times x squared, which is x cubed, and x times negative 3x is negative 3x squared, and then x times 1 is x. Also negative 1 times x squared is negative x squared. Negative 1 times negative 3x plus 3x, and negative 1 times positive 1 is minus 1, and this will be added to b times x cubed minus 3x squared plus x, because if you multiply this x to this trinomial, this is our answer. And of course, this will be added to c times 2x times x squared, so this is 2x cubed, and then 2x times negative x, we have negative 2x squared, and negative 3 times x squared, that is negative 3x squared, and negative 3 times negative x, that is positive 3x. And this is added also to our d times x squared minus x. So combining similar terms here, we have 5x cubed minus 16x squared plus 12x minus 2, this is equal to a times x cubed. And for this negative 3x squared with this minus x squared, this is minus 4x squared. And x plus 3x, that is positive 4x. And this will be subtracted by 1. Plus b times x cubed minus 3x squared plus x here. And of course, this will be added to c times 2x cubed minus 5x squared, because the negative 2x squared plus the negative 3x squared is negative 5x squared, and plus 3x plus dx squared minus dx. So distributing our constants to the polynomials, there we have a x cubed minus 4a x squared plus 4a x minus a, and this will be added to bx cubed here, and then minus 3b x squared, then plus bx, and added to 2cx cubed minus 5c x squared plus 3cx plus dx squared minus dx. So combining similar terms there, we have 5x cubed minus 16x squared plus 12x minus 2, which is equal to a plus b plus 2c quantity multiplied by x cubed, and this is added to minus 4a minus 3b minus 5c plus d quantity multiplied by x squared, and also added to 4a plus b plus 3c minus d quantity multiplied by x, and this is added to the constant, which is negative a here. So by comparison, we can say that the coefficient of x cubed at the left hand side of the equation and the coefficient of x cubed at the right hand side are equal, and that forms our equation 1. So 5 is equal to a plus b plus 2c, because these are coefficients of x cubed in both sides of the equation, and also the coefficients of x squared are equal also. So this forms our equation 2. So minus 16 is equal to minus 4a minus 3b minus 5c plus d here. And also coefficients of x are equal here, and that forms our equation 3. So 12 is equal to 4a plus b plus 3c minus d, and also the constants are equal from the both sides of the equation. So negative 2 is equal to negative a. Hence, from this equation 4, we say that a is 2. And then we can add equations 2 and 3. We have negative 16, which is equal to negative 4a minus 3b minus 5c plus d from our equation 2. And this will be added to equation 3, which is 12, which is equal to 4a plus b plus 3c minus d. So adding these two equations, we have minus 4, which is equal to this one, which can be cancelled, and this is minus 2b minus 2c, because this d and minus d cancels each other. So multiplying both sides of the equation by negative 1/2, we have 2, which is equal to b plus c. And this forms our equation 5. And substituting also a, which is equal to 2, to equation 1, we have 5, which is equal to a plus b plus 2c, but we know that a is 2 from here, plus b plus 2c. So subtracting both sides of the equation by 2, we have 3, which is equal to b plus 2c here. And this is our equation 6 this time. And solving equations 5 and 6, we have 5, which is 2, and that is equal to b plus c, when subtracted by equation 6, which is this 3, which is equal to b plus 2c. The result when you subtract is negative 1, which is equal to minus c, because the b cancels each other. So therefore our c is 1. And if c is 1, then therefore from equation 5 we can solve for our b, because in equation 5 2 is equal to b plus c, but c is already 1, therefore b is 1 here. And then you can solve for d from any of the equations 2 and 3 here. Now suppose we use equation 4, we have 12, which is equal to 4 times 2, because a is 2, is 8, and 8 plus b, which is 1, that is 9, and 9 plus 3 times 1, which is 3, is 12, and then 12 minus 12 is 0, therefore d is 0. And now that we have the values of a, b, c, and d, then we can substitute it here. So this is equal to the integral of a, which is 2 over x, and this will be added to b, which is 1 over x minus 1, plus c, which is also 1 times 2x minus 3 over the quadratic denominator x squared minus 3x plus 1 plus d, which is 0, and this 0 when divided by this denominator is 0. So simplifying our integrand here, this is 2 over x plus 1 over x minus 1 plus 2x minus 3 over x squared minus 3x plus 1 here, because this one will go away to 0. So applying the properties of integrals, that the integral of a sum is equal to the sum of its individual integral. So this is the integral of 2 over x dx, plus the integral of 1 over x minus 1 dx, and this is also added to the integral of 2x minus 3 over x squared minus 3x plus 1 here. And if we let our denominator x minus 1 as our u, we know that the du is dx, because the differential of x is dx and the derivative of negative 1 is 0. And of course, when you let v be equal to this denominator here, which is x squared minus 3x plus 1, we observe that our dv is 2x minus 3 dx here, because the derivative of x squared is 2x and the derivative of negative 3x is negative 3. So factoring this constant outside the integral symbol, we have 2 times the integral of dx over x, and this is added to the integral of du over u, because 1 dx is our du here, and this denominator x minus 1 is our u, and this is added to this one here, which is our dv, and our denominator here is our v. So evaluating these integrals, we have 2 times the natural log of x plus the natural log of u plus the natural log of v plus the constant of integration c, and substituting back our original variables, we have 2 times ln x plus ln u, where u is x minus 1 here, and plus ln v, which is this one here, x squared minus 3x plus 1, and this is added to the constant of integration c, and this is now our answer for this example here. Now let's proceed to case number 4, where the denominator of our rational function contains repeated irreducible quadratic factors. And in this case, you can see that our denominator is already in factored form, wherein it contains a linear factor and a square of an irreducible quadratic factor, because this quadratic factor cannot be anymore factored to linear factors, such that the coefficients are rational numbers. And you notice that this is already a proper rational fraction. Why? Because the degree of the numerator is 4 and the degree of the denominator is 5. Why 5? Because this is a quadratic raised to the power of 2. So we expect that this is having an x to the power 4 term. And when multiplied to a linear factor, the result will have an x to the power 5 term. Then therefore, this denominator is in the 5th degree. Hence, this integrand is a proper rational fraction. Therefore, we can now break it down into its equivalent partial fraction, which is a over x minus 1. And this is added to b times the derivative of this quadratic factor, which is 2x plus 4 over the quadratic factor x squared plus 4x plus 5 plus c over this denominator, which is x squared plus 4x plus 5. And since this quadratic factor is being repeated twice, we need 2 more as a partial fraction for this. So we have d times the derivative of this, which is 2x plus 4 over this quadratic x squared plus 4x plus 5, but this is raised to the power of 2, and this is added to the constant e over this quadratic factor, which is x squared plus 4x plus 5, but raised to the power of 2 dx. So solving for these partial fractions here, this is equal to x to the power 4 plus 9x cubed plus 33x squared plus 45x plus 12, which is over the denominator of x minus 1 times the square of x squared plus 4x plus 5, and this is equal to a over x minus 1 plus b times 2x plus 4 over the quadratic of x squared plus 4x plus 5 plus the constant c over this quadratic x squared plus 4x plus 5 plus this d constant times its derivative of the quadratic 2x plus 4 over the denominator of x squared plus 4x plus 5 when this is raised to the second power plus the last partial fraction over the square of this quadratic factor x squared plus 4x plus 5. And to eliminate these denominators here, we have to multiply both sides of the equation by the LCD, which is x minus 1 times x squared plus 4x plus 5 quantity squared, and multiplying this fraction by this expression here, this denominator cancels. So what remains is x to the power 4 plus 9x cubed plus 33x squared plus 45x plus 12, and this is equal to a times x squared plus 4x plus 5 quantity squared, because this denominator cancels with this one, and this is added to b times 2x plus 4 times x minus 1 times x squared plus 4x plus 5. Because this quadratic in the denominator will cancel with this 1 quadratic here. So what remains is this one times this one with 1 quadratic here plus c times x minus 1 times the quadratic x squared plus 4x plus 5, because again this quadratic cancels with 1 quadratic here. So what remains is c times x minus 1 with 1 quadratic here, which is this one, and this is added to d times 2x plus 4 times x minus 1, because the square of this quadratic cancels with the square of this quadratic, and this will be added to e times x minus 1. So we have x to the power 4 plus 9x cubed plus 33x squared plus 45x plus 12, which is equal to a times the square of this trinomial, and the square of this quadratic is x to the 4 plus 8x cubed plus 26x squared plus 40x plus 25, and you can check when you multiply this quadratic by itself, and then this binomial when multiplied by this binomial, the result is a trinomial. And this trinomial, when multiplied by this trinomial, we have 2x to the fourth plus 10x cubed plus 14x squared minus 6x minus 20. And this is added to our c times the product of this binomial and this trinomial. And the product is x cubed plus 3x squared plus x minus 5 added to the product of these two binomials here, which is 2x times x, which is 2x squared, and the sum of two products 4 and x, which is 4x, plus negative 2x, so we have plus 2x, and 4 times negative 1 is minus 4, plus ex minus e, which is from this one here. So distributing all our constants, we have ax to the fourth plus 8ax cubed plus 26ax squared plus 40ax plus 25a. And this will be added by this 2b x to the fourth plus 10b x cubed plus 14b x squared minus 6b x and minus 20b here, and added to this plus c x cubed plus 3c x squared plus cx minus 5c, and then added to 2d x squared plus 2dx minus 4d, and then this is plus ex minus e. So then x to the power of 4 plus 9x cubed plus 33x squared plus 45x plus 12 is equal to a plus 2b quantity multiplied by x to the power 4 plus 8a plus 10b plus c quantity times x cubed, and then added to 26a plus 14b plus 3c plus 2d quantity multiplied by x squared, and then added to 40a minus 6b plus c plus 2d plus e quantity multiplied by x, and then added to 25a minus 20b minus 5c minus 4d minus e here. So comparing the coefficients of the respective terms, we have the coefficients of x to the fourth are equal. So we have our equation 1, which is 1 equals a plus 2b. And also for the coefficients of x cubed, which is 9, should be equal to this one here. So 9 is equal to 8a plus 10b plus c. And then the coefficients of x squared are also equal. So 33 is equal to 26a plus 14b plus 3c plus 2c here. And also, coefficients of x are also equal. So 45 is equal to 40a minus 6b plus c plus 2d plus e. And lastly, the constants from both sides of the equation are also equal. So 12 should be equal to this one here. So 12 is equal to 25a minus 20b minus 5c minus 4d minus e. However, when x is 1, so when substituting to this equation here, we have 1 to the 4th, which is 1, plus 9 times 1 cubed, which is 9, plus 33 times 1 squared, which is 33, plus 45 times 1 is 45, plus 12 is equal to a times 1 squared, which is 1, plus 4 times 1, which is 4, plus 5 quantity squared, plus 0 here, because 1 minus 1 is 0, and 0 times anything is 0. And also this one, 1 minus 1 is 0, and 0 times anything is also 0. So that goes away. Also, x minus 1, so when x is 1, 1 minus 1 is 0, so this is also 0, and so with this one. So therefore, when we add 1 plus 9, which is 10, plus 33, which is 43, plus this 45, which is 88, and 88 plus 12 is 100. And this 100 is equal to a times 10, because 1 plus 4 plus 5 is 10. So 10 squared is 100. Therefore, a is 1. So when a is 1, therefore, from equation 1, we have 1 which is equal to a, which is 1 plus 2b, then b is 0 here. And also from equation 2, we have 9, which is equal to 8 times a, which is 1, plus 10 times b, which is 0, plus c. So 9, which is equal to 8 plus c, then c is 1. And also from equation 3, which is 33, which is equal to 26 times a, which is 1, so the product is 26, plus 14 times b, where b is 0, plus 3c, where c is 1, so the product is 3, plus 2d, this is d, so plus 2d, we have 33 minus 29, and 33 minus 29 is 4, so 4 is equal to 2d. Therefore, our d is equal to 2. So this is our value of d. And then from equation 4, we have 45, which is equal to 40 times a, which is 40, minus 6 times b, where b is 0, the product is 0, and then plus c, which is 1, plus 2d, which is 4, and then plus e. So here, 40 plus 1 plus 4 is 45. Then, therefore, 45 minus 45 is 0 here. So therefore, e is 0. Hence, substituting these values to our partial fractions here, we have the integral of a, which is 1 over x minus 1, plus b, which is 0, so that second partial fraction goes away, plus c, which is 1 over x squared plus 4x plus 5, plus d, which is 2 times 2x plus 4 over x squared plus 4x plus 5 quantity squared, and there is dx here. Because our e is 0, so we have only 3 partial fractions here. And we know that the integration of a sum is equal to the sum of its individual integration. So this is integral of dx over x minus 1 plus the integral of dx over x squared plus 4x plus 5 plus 2 times the integral of 2x plus 4 over x squared plus 4x plus 5 quantity squared dx. We have to simplify our second and the third integrand such that it will fit to the formulas that we have learned in the previous videos. So this is x plus 2 quantity raised to the exponent of 2 plus 1 squared, and you can check that this 1 is equal to this by completing the square, and plus 2 times the integral of x squared plus 4x plus 5 to the power of negative 2 times 2x plus 4 dx. And when we let our u be x plus 2, we notice that our du is dx. But here our a is 1 here. And also when our v is this quadratic trinomial of x squared plus 4x plus 5, we notice that our dv is just 2x plus 4 quantity dx. So by substitution, we have the integral of dx over x minus 1 plus the integral of du over u squared plus a squared plus 2 times the integral of v to the power negative 2 dv, then the integral of dx over x minus 1, when you get the derivative of x minus 1, is dx. So therefore, the integral of this is the ln of x minus 1, and plus 1 over a, and because a is 1, so this is 1, times the arctangent of u, which is x plus 2 over 1 plus 2 of the integral of v to the power negative 2, which is v to the power negative 1 over negative 1. So this becomes minus 2 over the v, and the v is x squared plus 4x plus 5, and this is added to the constant of integration c. So therefore, this is our answer for this example in case number 4. So the answer is the natural log of x minus 1 plus the arctangent of x plus 2 over 1, which is x plus 2, minus 2 over x squared plus 4x plus 5. And this will be added to the constant of integration c. And that's it. If you learned something today, please check out my channel for more videos like this and click subscribe. Click the notification bell below so you'll get notified whenever I'll be posting a new video. Don't forget to like this video to show your support. And always remember to math your way up. Thank you.